This is a review of acids and bases. As you see in the mean, what did one titration say to the other? Let's meet at the end point. In this review, we'll talk about the difference between the end point and the equivalence point. Okay, conjugate acid-base pairs. Conjugate bases are what's remaining of an acid after the acid loses its proton, which we think of that being an H+. And then if a base is gaining an H+ or gaining a proton, we call that a conjugate acid. So notice on both sides of the reaction, there's an acid and a base. So there are two acids in the reaction and two bases. So the acid forms a base, and the base, by gaining the H+, forms an acid. There are 6 strong acids. Make sure you know these. Their conjugate bases, which would be chloride, bromide, iodide, nitrate, sulfate, and perchlorate, are such weak bases that they can't even react with water. So these we will commonly see, especially chloride and nitrate, as spectator ions. So they're not able to react with water in the solution, so they end up just being spectator ions. With strong acids, these 6, the equilibrium lies far to the right. If a Ka was given, we typically don't see Ks for these. It would be greater than 1, much greater than 1, which is a completion reaction, because these are completely ions in the solution. So, and we call those strong electrolytes when they're completely ions. These solutions, since there would be so many ions in the solution, would be good conductors. If you're asked to calculate the pH of a strong acid, just take its molarity, plug it into the pH formula, the negative log of H+, and remember H+ and hydronium ion are interchangeable, and you have the pH. For weak acids, really, it's not that you need to memorize a bunch of these. It's basically any acid that's not one of those 6 strong acids. And really they are, besides being acids, everything's different about them. Equilibrium lies far to the left. They have less than 5% ionization. They have really small Kas, since they're mostly the molecule. And if you're comparing Kas, the smaller the Ka, the weaker the acid, the fewer ions it's forming. Their conjugate bases are relatively strong, and they can react with water. So I've given the example of acetic acid, written as the organic chemist would write it, CH3COOH. You might be used to seeing it as HC2H3O2. So again, same acid, written 2 different ways. And then the conjugate base is acetate. Weak acids exist mostly as the molecule in the solution, since they have this less than 5% ionization. So if you're told you have a weak acid in a reaction, make sure you write the weak acid as the whole molecule, whereas with the strong acids we would write those as 2 separate ions. So again, weak acids write the whole molecule. When we're asked to find the pH of a weak acid solution, it's not that simple. We have to go through an equilibrium problem. A rice table is really helpful to keep up with information. And at the end of the rice table, once we know how much H+ or hydronium ion has formed in the solution, then we can use the pH formula. So it's more of a process. On the AP formula sheet, there's some reminders about what K and Kb expressions look like. We'll talk about Kb in a minute. Notice we have the relationship of Kw at 25 degrees Celsius, which is H+ times hydroxide ion, and also that Kw equals Ka times Kb. There's our pH and pOH formula. If we add pH and pOH together, we get 14. This is our buffer relationship. And then just, again, some other reminders, because we can be given pKa values. Really, if you see a P in front of anything, it's the negative log of that value. So as you notice that pattern here. One other thing that's not on here that I want to point out is pKa plus pKb also equals 14 at 25 degrees Celsius. And that could be helpful possibly when you're talking about certain types of titrations. So let's figure out let's go over a reminder of the pH of a weak acid. So first we're asked to write the equilibrium expression for the reaction below. Then the question is to calculate the pH. Notice the solution, we're given the molarity of the weak acid solution, and we are given its Ka. So set up your equilibrium expression. You have the guideline on the formula sheet. Notice it's products of reactants. We don't include pure liquid, so we need to leave out the water, and we'll have just the acetic acid as our denominator. So we set that up, and then to get our to calculate the pH, we need to set up a rice table. So again, we have our reactants, and then I've already filled in the initial line. So initially, we know that we're starting off with this 0.3 molar solution of acetic acid. There's nothing mentioned about the hydronium ion or the acetate ion, so those are assumed to be 0. So now we need to think about the change line. So as the acetic acid does form a few ions in the solution, notice the mole ratios are all 1 to 1 to 1, so they're all the change for acetic acid. Will be the same change for the hydronium ion and acetate, but those will have to increase and so that we can figure out the pH. So we'll continue filling out our table, and notice you'll have -x, +x, and +x since all those have the same mole ratio. Then we get down to and do the math down each column. So we have 0.30 minus x, and again, since this x is so small, we're going to assume it is negligible, so we'll just use that as 0.30. Otherwise, we'd end up using the quadratic formula, and that's not required on the AP exam. So let's simplify it and make our life a little easier. So when we set this up, we have x times x, or x squared over 0.30. The Ka was given, so that's plugged in 1.8 times 10 to the -5th. Solving for x, which in this problem, x was the concentration of the hydronium ion, and it was a concentration of the acetate ion, but it's that hydronium ion value that's going to help us with the pH, so we take the negative log of that, and we get 2.64. Very classic example. Could be a multiple choice question. They would, since we're taking the square root, if it was on multiple choice, it would have to be a simple number like 4.0 times 10 to the -12th or something like that, where we could take the square root of 4 in our head and get 2, and then take half the exponent. So that would be 2 times 10 to the -6. So anyway, kind of a classic multiple choice question as well. We could be asked about percent ionization or dissociation, and really it's, if you think about in the previous problem, we started with, and I'm going to go back to that, we started with the initial concentration of the acid was 0.30. The amount that it's going down by is, that is our change line. That is what we need to have, and because that's the part of the acid that's dissociating. So I think of anytime I think of a percent, it's like part over whole times 100. So the part of the acid that's dissociating, which also ends up being the hydronium ion concentration, divided by, what did we start with? The whole amount of acid at the beginning times 100. So notice I've plugged in 2.3 times 10 to the -3rd divided by 0.30 times 100 is such a small percent. It does have to be less than 5% for us to neglect that minus x. There are other acids we call polyprotic acids, or you might see the term diprotic. Diprotic would also refer to carbonic acid, since carbonic acid does have 2 hydrogens. But if you had like phosphoric acid, which is H3PO4, that would be considered polyprotic because it has many hydrogens that it would lose one at a time. So that's what's a little different about polyprotic or diprotic acids, is that they have more than one proton or H plus that they will lose to the solution, and they lose these in subsequent steps, so they're lost one at a time. The largest dissociation will always occur in the first step, so Ka1, notice these have little Ka1 and Ka2, they have values, and that refers to the dissociation step. So when the first hydrogen is lost, H plus is lost, it's called the Ka1. Then the ion that's formed here, where there's still an H plus remaining, it can also go through a dissociation. But again, since this first step doesn't happen to a great extent, then the second dissociation is going to happen to even much smaller extent. Again, Ka1 is always greater than Ka2. Here are some classic questions that could be asked on multiple choice. Which species, other than water, is present in the solution the highest concentration? And then same question, but present in the lowest concentration. So if you think about it, if it's a weak acid, and we've said, several slides back that when we have a reaction, we always write a weak acid as its whole molecule and not separate ions like we do with strong acids. And it's because it's mostly the molecule. It has less than 5% ionization. So that should help us be able to answer the first question. So carbonic acid would have the largest concentration other than water. And then the lowest concentration always go to the end of the last dissociation step to the last ion that's formed. So our lowest concentration would be carbonate. For strong bases, most likely you're going to see a group 1 metallic ion with hydroxide. There are some group 2 ions that would also be with hydroxide, like calcium ion, strontium ion, or barium. These do have some solubility issues. They're not super soluble. So group 1 metals are typically the most common: lithium hydroxide or sodium hydroxide or potassium hydroxide. And like strong acids, these are strong electrolytes when they're dissolved in water. They're great conductors of electricity. Again, any solution that has lots of ions would be a good conductor of electricity. They exist totally as ions in an aqueous solution. Now, when we're asked to find the pH of a strong base, we do need to plug in its molarity, but since it's contributing hydroxide ions to the solution, by taking the negative log of that, we're actually getting POH, so we do have one more step. So 14 minus the POH does give us the pH. I give an example of kind of one type of problem that could be tricky. So sometimes they'll give you one of those group 2 hydroxides, like barium hydroxide, and they'll give you its molarity, and then they'll ask for the pH of that solution. Just be careful, because when this barium hydroxide breaks into ions, it actually has 2 hydroxides for every one of its formula unit, so you would need to double its molarity. So its actual molarity for the hydroxide ions in the solution would be 0.040 molar. Take the negative log of that, you get 1.40 for POH, subtract from 14, and it's 12.80. So high pH means a basic solution, but again, if you did not double that, if this was multiple choice and the numbers were pretty easy, there would be an answer that looked correct without the doubling. So the doubling of that hydroxide ion is super important. For weak bases, ammonia is the most common weak base, and then you'll see some unusual carbon compounds that contain nitrogen. Just like weak acids, equilibrium lies far to the left. Because they're bases, we have Kb values. These Kb values are less than 1. Again, just like when we talked about weak acids, the smaller the Kb, the weaker the base. Their conjugate acids are relatively strong, and when we say relatively strong, we mean they can react with water. Since ammonia is the most common weak base, its conjugate acid is the ammonium ion. Just like with weak acids, weak bases exist mostly as the molecules in solution. So if you're asked to write a reaction with a weak base, you make sure you write the whole formula. Do not separate it into ions. And then to find the pH of a weak base solution, it's a process. We have to do an equilibrium problem. You have a Kb, make a rice table, and then it goes from there. Now, water is amphoteric, and there are other substances are as well. And really just the definition of that is that it's a substance that can either act as an acid or a base. So water could gain an H plus and form the hydronium ion, which means it's acting as a base, or water could lose an H plus and form the hydroxide ion, which means it's acting as an acid. So it can do both things. Here's the Kw value, which is really the equilibrium constant and W does refer to water, at 25 degrees Celsius. One thing to note is that this reaction, which we call the auto-ionization of water, and again, you can tell that it's not happening to a great extent because that Kw value is so small. But this reaction is endothermic. So if the temperature increases above 25 degrees Celsius, we're going to expect, based on Le Chatelier's principle, that equilibrium would shift forward. It would form more ions, more of each ion. And since it's the hydronium ion that controls the pH, if you have more hydronium ion, that actually makes the pH go down, be even more acidic. Because at 25 degrees Celsius, the pH of water is 7, but at a higher temperature, we'd expect it to be a little acidic. So just as just something to hopefully remember. Here's the KW relationship with the ions that we saw on the formula sheet. And then there's our pH plus POH relationship. Salts. Every time we have a neutralization reaction, like an acid plus a base makes a salt and water. A lot of salts are completely soluble and don't react with water, don't affect the pH, but there are some ions in salts that can react with water and can affect the pH. So how do we know? How are we supposed to know? Well, the easiest way to think of this is we know 6 strong acids, and we said that their conjugate bases were worthless, meaning they can't react with water. So if you look at anions, and they came from one of those 6 strong acids, so that would be chloride, bromide, iodide, nitrate, sulfate, or perchlorate. If you see those in a salt, you know those are very, very weak bases. They can't really react with water, so they stay dissolved in the solution, and nothing's going to happen to the pH based on those anions. The other part of a salt would be the positive ion or the cation, and again, it's the same thing. When we have a strong base, the positive ion that was in the strong base, like lithium ion or sodium ion or potassium ion, those are really worthless conjugate acids, so they're going to stay spectator ions. They also can't change the pH. So these are the 2 groups that will not affect the pH. So again, this just kind of goes through it with a specific example. So if I had a salt that contained chloride, so let's just say, well, I'll just give you one. Let's just do NaCl. So if I have sodium chloride, we can see chloride is an anion that's associated with hydrochloric acid, which is a strong acid, so that tells us that the chloride part of the salt can't react with water, and that would cause the pH to stay 7. So then I have to look at the other part of the salt, and here is sodium ion. Again, sodium ion, you think of it as a spectator ion, so that might help you to remember this, but it also is associated with a strong base, so it is not a good acid. It can't react with water. So this tells you that since the sodium ion and the chloride ion both came from a strong base and a strong acid, neither of those ions could react with water, so that the pH of that solution would stay 7. But when we have a salt, like if instead of having sodium chloride, if I had sodium nitrite, which, be careful, that's not nitrate, it's nitrite, I would know that the sodium ion couldn't react with water, but the nitrite ion, as we see here, if I put a hydrogen in front of that, that's a weak acid. That's not one of my 6 strong ones. So because it's associated with a weak acid, nitrite ion, it should remind me that, oh wow, that is a conjugate base that could react with water, and so that would cause the solution to be basic. Okay, and I'll write that reaction at the bottom. So nitrite ion plus water, and the way I help my students remember it is, because they look at this and sometimes they struggle with what do I do, focus on the charge. If this is a negative charge, that means that to have this whole reaction be balanced, I'm going to have a negative on the other side. So if I add nitrite ion to water, that means that it's going to form hydroxide with water, and then that hydrogen is donated, and there we end up with that weak acid we were talking about. So because hydroxide ion is produced, this is a basic salt. So it wasn't the sodium ion that did anything. Notice I just crossed it out, and then I could focus on the nitrite ion. Think of that reaction. I say, oh, that's a negative ion associated with the weak acid. It will react with water. It will make a basic solution, which has a pH, as you can see, greater than 7. Okay, let's move on to a cation that would affect the pH. So we said that the ammonium ion, or ammonia, is the most common weak base. So what happens when its ammonium ion is part of a salt? So let's take ammonium, and I'm just going to mix it up, and I'm going to add it to nitrate. Again, I chose nitrate since nitrate is, based on solubility rules, we know it's always a spectator ion, but even going a little deeper, it can't react with water because it's associated with a strong acid, meaning it's a worthless conjugate base. So I'm going to mark out the nitrate ion, and I'm going to look at my ammonium ion reaction, and I think, well, ammonium ion came from the weak base ammonia. It can react with water. And again, just like I said before, think, well, if it's reacting with water, and I have a positive sign here, I'm going to have a positive ion on the other side so I can keep not just the atoms balanced on both sides of the reaction, but also the charges. So when that tells me that the ammonium ion is going to donate a hydrogen to the water to make hydronium ion, so there's how I get my positive charge. And then what's left of the ammonium ion is ammonia. So notice this conjugate acid is making its weak base, just like we saw the conjugate base making its weak acid on the other side. So there you go. So that's why we have acidic pH, or the pH is less than 7. Now, a buffer. We talk about salts before we talk about buffers, because if we have in the solution a weak base and its conjugate acid, or a weak acid with its conjugate base, that means we have a buffer present. So remember, a buffer has two components. We say weak acid and conjugate base, but really it's a weak acid and it forms a base. So the word conjugate just means it comes from the acid. So you don't really even have to use that. So just remember, a buffer has a weak acid and a weak base, and they're associated with each other. Their formulas look related. What we really need to be able to do is what happens, and we have to be able to predict this, if we add H plus to a buffer, what part of the buffer is what you need to decide. What part of the buffer does it react with? So think, here's a buffer, a weak acid and a weak base. If I add H plus, think H plus is an acid. Do acids react with acids, or do acids react with bases? And we know that acids react with bases, so that's why it's saying that H plus reacts to completion with the weak base. Okay, so you might have to choose which one the H plus would react with. And then if we take the adding hydroxide ion to the buffer, now we're adding a strong base. And again, if the buffer, as you see, is circled, is a weak acid and a weak base together, which part of that would the hydroxide ion react with? Well, a base is going to react with an acid, and so that's why I have this statement here. So to determine the pH of a solution, we really need to know, and here's that pKa term, which we know is the negative log of the Ka, plus the log of whatever the concentration of the base part of the buffer divided by the concentration of the acid part of the buffer. So here's an example problem. A buffered solution contains 0.25 molar solution of ammonia. There's a Kb, and a 0.40 molar solution of ammonium chloride. Notice ammonia, ammonium chloride, they sound related. That's a buffer, okay? Because you've got the weak base. We know it's a weak base because it has a Kb, and then the ammonium chloride as well. So if we're just calculating the pH of the solution, and we have the Kb, now this is the one time, there is a version of this formula that has POH equals pKa. I'm going to write it down. I do not get my students to memorize this. I just, there's too much to know for the AP exam. If you remember it, that's great. The problem is it's flipped over. This is acid, whatever the acid part of the buffer divided by whatever the base. It's in all textbooks. You're welcome to use it, but there's really no need to memorize that, because if we have Kb, we can always convert Kb to Ka. So the way I teach my students to do it is we just take the KB and we divide it into the KW. And actually, I'm going to do that on the next slide. I know this is a little messy. I'll just kind of give you the formula. I've just rearranged it from the formula sheet. So if I do that division KB into KW, I'll have Ka, and then I can just use this one formula that's on the formula sheet, no matter if I have a weak base or weak acid solution. It will always work. So again, not necessary to remember that. If you already know it, great. If you don't, just use this. It's on the formula sheet. It'll make your life a little bit easier. So let me walk you through how I would set that up. So as I said, we've got to change KB to Ka. So if we know Ka times Kb is 1 times to the negative 14th, that's on the formula sheet. As you saw, I had already done. I just rearranged it. If Ka equals the Kw value divided by the Kb given, and that gives me, doing the math, 5.6 times 10 to the negative 10th. So then I go back to my formula. pH equals the negative log of 5.6 times 10 to the negative 10th plus the log, and again I have to make sure I have the numbers in the right order. The base is on top, so ammonia is my base, divided by the ammonium ion, which is my acid. So dividing, taking the log of that term plus the negative log of the Ka, and I get a pH of 9.05. That makes sense. It's basic. This is a weak base. Now a titration. Titrations, you might have done one, a couple maybe this year or maybe in your first year class, but this formula where moles of acid equals moles of base, remember that, and with my students I call this the equivalence point formula. Because in a titration, the place where the moles of the two reactants are equal, the acid and the base you're adding together, that is at the equivalence point, and that's usually the whole point doing a titration is to know, some information about the equivalence point. So again, in a multiple choice question, they may not mention the equivalence point. They might say you have complete neutralization. That's a clue you're at the equivalence point. But we're going to use this formula. Again, we'll know 3 of the 4 numbers, and we'll be solving for the 4th, whatever that is. Now, one of the volumes you might have to get from a graph. You might be told a volume of maybe an acid you're starting with, and the volume at the equivalence point you might have to read from the graph, but you would have been given a titration curve to come up with that information from it. So here are a couple curves. So notice this is a strong acid, this is a weak acid. And again, we should be able to tell this from, and I said not, and I asked the question, what are 2 distinct differences other than the shape? Because if you notice this, the beginning of this strong acid, it has a gradual increase, it has a much larger equivalence region, and then this weak acid, it's going to have kind of this more of a increase, and then it just gently goes up, but its equivalence region is shorter. That's not really the shape. There's other important points of the curves that are very different, so that you really need to know. So what are those? And I'll just, really what it's going to be is where it starts. So hopefully you notice that. A strong acid should have a pH that's relatively low, like less than 2, I would say, and then a weak acid is going to be above 2. The other huge thing you should point out is the equivalence point. A strong acid, strong base reaction will have an equivalence point with a pH of 7. Okay, and no matter what this is, let's say this is HCl in my beaker. No matter what this strong acid, strong base reaction is, the net ionic reaction is H plus OH minus yields water. And so what you need to remember is the product is what controls the pH of the equivalence point. Because as we said, at the equivalence point, the 2 reactants, in this case we have H plus and OH minus, the 2 reactants are equal and actually are 0. Okay, so it's the equivalence point that's controlled by the whatever products are there. So we have, in this case, we'd have a soluble salt, Na plus and Cl minus. Only water's controlling this pH, and that's why it's 7. When we have a weak acid strong base reaction, notice that, and again, this could be something like, let's just say it's HF, just to make it a simple formula. HF is a weak acid, and it's titrated with sodium hydroxide. So since, HF is a weak acid, so I'm going to write its whole formula. If I write its net ionic, sodium hydroxide, again, sodium ions are always spectator ions, so I just leave off the Na+. Notice this makes water. However, that's not the only product that's there. It also makes fluoride. And so if you notice, this equivalence point is basic. And this goes back to the salts we talked about. Fluoride is an ion that is associated with a weak acid. It reacts with water and forms a little hydroxide. So again, it's the products that are controlling the pH at the equivalence point, because the reactants are equal and actually have gone to 0. So if we superimpose a weak acid curve on top of a strong acid, this is what it looks like. Notice that these curves completely line up and come together after their equivalence point. Their equivalence points are different, their beginning pHs are different, so that tells us they're different acids. But if these two acids come together at the same equivalence point, and what this means is this is the volume of base it took to react completely or completely neutralize each acid, what does that really tell us about each acid? And it tells us that they must have had the same beginning molarity, because again, here's our relationship, MaVa equals MbVb. So if it's the exact same base for both, and each acid requires the same amount of base, even though they have different beginning pHs, they must have both had the same beginning molarity. Okay, so notice when you look at a curve, always go to the beginning and say, okay, where am I starting? It's above 2. The equivalence point is above 7. That confirms this must be a weak acid. And because it's a weak acid, we need to know where the equivalence point is, and we need to know that volume. It looks like it's around 10. If I take half this volume here and I go to where that is half on the graph, notice, and I go up to the curve, we call that the half equivalence point. And this is a special place in a weak, any kind of weak, strong titration, because this is where pH equals pKa. And the reason those two are equal is because if you go back to the buffer formula, the whole formula on your formula sheet is pH equals pKa plus the log of base divided by acid. What's happening here, this is the place where you have the exactly equal parts of the buffer. So if you have equal amounts in that ratio, the log of, let's say, 0.1 divided by 0.1, it goes to 1, so the log of 1 is 0. So what's left of the formula here is pH equals pKa. So what you need to know is, at the half equivalence point, this is true, and this is where we have equal parts of the buffer, or this is the maximum buffering capacity is the way it's referred to as. So that's pretty important on these titration curves. Typically you're asked about this half equivalence point. So again, I found the volume of the base at the equivalence point. I took half of it, where that goes to the curve. This is a really easy way to find the Ka of the weak acid. I would just say 10 to the negative pH, and that would tell me the Ka. So here's a titration where it's flipped it around. Now we have a weak base titrated with HCl. Now you're told that, but again, if I look at the equivalence point, I notice that it's acidic. And again, it's because, and I'm asking a question in just a second, but we'll look at why it is. So it says, in this titration of ammonia with hydrochloric acid, what species is present in the greatest concentration at points A through E? Where's the half equivalence and equivalence points? And what species controls the pH at point F? The best thing to do is to write the net ionic equation. So we know we have ammonia plus, and again, if I have a strong acid, I don't write it together. I only write H plus, and so that makes ammonium ion. So, as we think about this, at point A, notice 0 HCl has been added. So what is the greatest species in concentration at point A? Well, it would have to be the weak acid, because that's it's in there with water. Again, we're leaving off water with these. And then when we get to point B, what you need to think of is once we start adding a few drops of H+, as we said on that one slide, the H+ that's added gets completely neutralized by ammonia and is making the ammonium ion. So at point B, we still have more ammonia than ammonium ion, and the way I know that is because point E is the equivalence point. If I take half of 60 and go up to 30, that tells me that C is the half equivalence point. So if C is the half equivalence point, that's where these two are exactly equal. So if I'm before the half equivalence point, I've got more of the reactant in H3, and then what do you think about after the half equivalence point? It switched. More of the ammonia got reacted, and now I have more of the ammonium ion past the half equivalence point. Okay, so at A we have mostly NH3. At B we have a little bit more NH3 than NH4+. At C we have equal amounts of NH3 and NH4+. At D we have more NH4+ than we have of NH3. When we get to point E, these two are equal and 0. It's the ammonium ion that's controlling the pH. And again, notice the pH is acidic because, as we said, ammonium ion is a positive ion. It will react with water. It will make hydronium ion in the solution. That's why we have, remember, the products control the pH at the equivalence point. So we already said the half equivalence point was C, the equivalence point is E. And so what is controlling the pH at F? And notice it's getting really low, and it's because during the titration we keep adding whatever's on the x-axis is in the burette. We keep adding that. So once we get past the equivalence point, as I've marked these out, the two reactants are exactly equal, but so there's no more ammonia, but what do we keep doing? We keep adding H+. So it's H+ that's controlling the pH. In a titration, we can use an indicator. An indicator is it's really a weak acid itself, but it has a color change at a certain pH, and it depends on the indicator as to when that happens. But when an indicator changes color, that's what we call the endpoint. So if you're going to use an indicator for a titration, the goal is to pick an indicator that's going to start changing colors around the equivalence point pH of your titration. So we'd want the endpoint to align with the equivalence point. So really what that boils down to, and this is what you really need to know, is you want to choose an indicator with the pKa, because that's the negative log of Ka, that is close to the pH at the equivalence point. And that shouldn't be there.